Bismillahirrahmanirrahim. Students, our today's topic is about the general implications of band theory of solids. In this topic, we basically cover two things. One is how many number of states or number of electrons or number of wave functions that are exist in a single band. And the other thing is how band theory can be used to distinguish between conductor, insulators, and semiconductors. So first of all, we look on the first part of our discussion. How many number of bands, number of states or wave functions or number of electrons that are present in a band. Its derivation is very simple. If you have a linear crystal having length L and boundary condition may be written as psi of x plus L is equal to psi of x. And if you apply the block function, then you can write it like this: psi k of x plus L is psi k of x exponential iota k L. So these two conditions, by comparing these two, this can only be achieved if exponential iota k L is equal to 1. So we want to see how exponential iota k L can be 1. So if you use other formula, then it can be written as cos k L plus iota sin k L is equal to 1. So this can be possible if this KL is equal to 2 and 5. Right? So from here you can find the value of K is equal to 2 and 5 by L. Here small n is integer and it gives you the information about the number of states or the number of wave functions that exist in any given band or number of K values. So you can easily find the number of K values using this relationship. To find exactly what are the number of possible states, you can rewrite that relationship to find the value of small n is equal to KL divided by 2 pi. So take differential for the interval dk. So how many states exist in an interval dk? So take the differential, dn is equal to L over 2 pi is constant dk. So for the complete band, what are the total number of wave functions or total number of states that are existing? So you have to take the integral of it. So n is equal to integral dn. So put the value of dn from the above equation, you get L over 2 pi. Apply the conditions of first Brillouin zone minus pi over a to pi over a, because the first discontinuity occurs at the boundary of the first Brillouin dk. Okay, simply integrate it and put the values. Doing simple L over a as answer. So from this n is equal to L over a, so L is equal to n. A will be your answer. If you have crystal whose length is L, and in that length it has capital N unit cells. So if you have capital N unit cells, so you can write L is equal to Na. So using these two relations, L is equal to small na and L is equal to capital Na, we reach to the conclusion that small n and capital are same. So number of wave functions are equal to the number of unit cells that are existing inside of a crystal. So the total number of possible states in a band is equal to number of unit cells in its system. One more thing is important in that situation. So according to Pauli-Exclusion principle, each energy state can be occupied by two electrons having opposite states. So electron exists in pairs, one with spin up and other with spin down. So each energy state can be occupied by two electrons. So each field energy band can have maximum how many electrons? 2 multiplied by n. So double to that of number of unit cells that are existing inside the unit cell. So this is our discussion about the number of energy states, number of electrons, or number of wave functions that exists in a single band that form the band actually. Now we want to see that how band theory can be used to distinguish between metal, insulator, and semiconductor. So we have to discuss various points regarding this issue. So we start from over there that how the conductor, insulator, and semiconductor have different electrical conductivity. So to achieve this, we introduce a factor which is the ratio of rest mass to that of effective mass of the electron. So a factor is Fa, which is equal to m divided by m steric. So put the value of m steric, you get it m divided by h cut square into d square v by dk square. So if you want to define this factor Fk, so it gives you the measure of extent to which an electron in a state K is free. So how you check this factor and what it gives you in return? So the outcome is the extent to which an electron is free. So if the extent is higher, then the chance to have free electron is higher, then the conductivity should be higher. If the extent of finding free electron is low, then chance of having conductivity is also low. So for the case if m steric is greater than n, it's quite simple. So you have this ratio. If in this ratio, if m steric denominator is greater than numerator, so it means that effective mass is higher as compared to that of the normal mass. So it means that electron appearing as a heavy particle. So it is difficult for a heavy particle to move. So it indicates that the conductivity in that case should be low. So if m steric is equal to m, then in that case you get extent is equal to 1. Means both effective mass and normal mass of the electron are same. This is only possible if electron is a free electron. So if electron is a free electron, it means that the conductivity in the material having a free electron should be very high. So by analyzing this factor Fk, you can analyze that whether this material have good conductivity or a bad conductor. So if you are relating Fk with m steric or effective mass, so the variation which we saw in the value of m steric or the effective mass should also appear in this factor Fk. So if you draw Fk and diagram or dispersion curve with K, which is shown over there in this slide. So you see that as for the effective mass is positive for the lower half of the band and a negative for the upper half of the band. So the same effect actually happens to this factor Fk. So it has positive values for lower half of the band for smaller values of K, and it has negative values for higher values of. So when it has negative value, then we can say that we are dealing with that holes in regard to the electrons, or you can say we are dealing with the positions where there is an occupancy of electron, the absence of electron. So now we consider field band, energy band filled with electron up to K is equal to K1. As you can see in this diagram, K is equal to K1. This might be point of inflection. So this is a position up to that point the band is filled with the electron and the upper part of the band is empty. So to calculate the conductivity of the material, we like to know the effective number of electrons in the band. We have to know the actual extent to which how many electron effectively exist in the band. So extent of finding free electron is Fk. If you sum all the extent, then you get n effective. So where the summation extend over all occupied states in the band, right? So for one-dimensional lattice of length L, we have states also considering Pauli exclusion principle. You had dn is equal to L over pi dk. This is the same relationship we have written in our initial slides. The only difference is there you write L over 2 pi because at that point you are not considering Pauli exclusion principle. So here you consider Pauli exclusion principle, so value is doubled. So you get dn is equal to L over pi d. Okay, so from this relation you can find the number of electrons, number of states that are exist in the band. So here is a simple and small derivation to find the effective values. So you have applied integral from k1 minus k1 to plus k1 fk dn, right? Okay, so put the value of dn, L over 2 pi is constant, that come out, and that is m over h cut square. D square is over dk square is the value of fk. So this is quite simple. Solve this integral and for the value k is equal to k1. You get here you double the value because it is definite integral. So you change the limit from minus k1 to k1 from to 0 to k1. So all you have to do is to double the value. So you got k is equal to k1. So this is the final relationship for n effective. No, at the boundary of the zone, at k is equal to plus minus n pi over a, which in our case should be pi over a or minus pi over a, boundary of the first Brillouin zone. So these are the points where the slope of the EK diagram will be 0, as you can see in this diagram. At these points, the slope will be 0, dE by dk will be equal to 0. So if dE by dk is equal to 0, so effective number of electron exists at the boundary will be 0. So there is no free electron exists at the boundary of the band. So thus the effective number of free electron at the zone boundary is 0. Moreover, this relationship dE by dk will be maximum always at the point of inflection of the AK curve. So at point of inflection, you have maximum number of free electrons available for the conduction process. So we can differentiate between metals, insulators, and semiconductors at this point. So we are in a position to differentiate. So first of all, an insulator. A solid is an insulator if certain number of bands in it are completely filled and the rest are completely empty. So it have completely filled energy bands or completely empty energy bands, right? This is generally true at absolute zero. At when temperature is not equal to zero, it may be possible that some insulator may start slight conduction. It depends upon the gap between the allowed bands. So if gap is higher, then the filled band, which is usually called valence band, and the completely empty band, which is called conduction band. So it depends that you can provide energy of the electron which is in the valence band so that it reaches the conduction band. So if this is possible, then this can be achieved. If this is not possible, then this cannot be achieved. So there are few insulators which show slight conductance at room temperature. We will discuss that case later on in the end of this slide. So now we discuss conductors. Solid will be conductor if it has incompletely filled bands. So in insulator, you have completely filled or completely empty bands. So in conductors, you have partially filled bands. That is, there are empty states just above the filled level. So bands, all the bands have a slight number of electrons. 3 electrons are there. So there should be some conduction. Now we talk about intrinsic semiconductors. Semiconductors are very much like insulators if the temperature is 0 Kelvin. However, at room temperature, these are the insulators in which 2 electrons from filled valence band jump up to the conduction band, which is initially empty at the room temperature. Although there are few electrons in the conduction band now, so initially at 0 Kelvin, the valence band is filled, conduction band was empty. At room temperature, some of the electrons thermally get sufficient energy to jump up to the conduction band, but these electrons are very low. So the only difference between conductors, semiconductors and insulator is the band. So the semiconductor have very small band gap of the order of few electron volts, so that with the small amount of energy you can transfer an electron from valence band to the conduction band to have slight conductivity. So their conduction is low, but they are conducting. So their properties are in between conductor and insulator. That's why they are called semiconductors. So we have to note that all the semiconductors are the insulator at 0 Kelvin. So all semiconductors show no conductivity at 0 Kelvin. So they are very much like insulator, and they show slight conductivity at room temperature. So they behave like conductors. So they have properties in between conductor and insulator. So we call them semiconductors. Okay. Most of the insulators have larger band gap. So they did not conduct at room temperature because of this larger forbidden gap. So it depends upon the forbidden gap that material will be conductor or material will be insulator or material will be a semiconductor. This can be seen from these diagrams as well. If you see this first diagram, which is marked as 11.23, this is your valence band, which is overlapped and like this, which is overlapped with the conduction band. So some of the electrons in the valence band are also part of the conduction band. So in that case, either both the bands are partially filled or both the bands are partially empty or both the bands are overlapping. If you see this diagram, 11.24 and its part A for the diamond, which is an insulator. The valence band is completely filled as it is shaded completely. The conduction band is completely empty because there is no shading. And there is a band gap of 5.4 electron, which is a sufficiently wide band gap to class it as insulator. If you see silicon, which is a intrinsic semiconductor, in case of intrinsic semiconductor, you see that valence band is completely filled, conduction band is completely empty, very much like the insulator, but the only difference is the forbidden energy gap is as small as 1.1 electron. So this band gap is quite small that even at room temperature, some electrons have sufficient energy to jump from valence band to the conduction band and overcome this energy gap between valence and conduction band. So that's why semiconductor at room temperature is so shows light conductance. And this is a more realistic view of the band structures of different materials. So the first diagram is for insulator. A similar diagram will be for the semiconductor. The only difference will be the gap between at these two points over there, between this and this. This is the region which is showing the gap. So if this gap is larger, then this will be an insulator, and if this gap is smaller, then this will be a semiconductor. So if you see the diagram B, this is for a metal or a semi-metal. Semi-metal have slightly lesser number of states as compared to metals. They show conductivity, but conductivity is not as good as that of the metals or good conductors. So here you see that conduction and valence bands are partially filled. But if you see the level, that level of electron in the valence band is equal to level of electron in the conduction band. So it verifies the existence of overlapping. Or if you see the diagram C, here you see at the zone boundary, the valence band is filled and conduction band is partially filled, slightly filled. So there are already some electrons exist in the conduction band. So one thing to be noted that as in figure B, the overlap need not to occur along the same direction. जैसे like you see in C diagram, along the same line. So here you see that they are not up above each other. So here at this point you may see a small difference, but there is no gap. The bands are actually overlapping. They are crossing each other, but not along the same direction. They exist at different positions. Overlapping exists at different positions. So along the same direction in the Brillouin zone, if the overlap is small, we relatively have two states involved, and we called it semi-metal. And if overlapping is large, we have more states involved for the conduction. More states are overlapping, so we called it metal or a good conductor. This is all for today's discussion. So if you have any question, you can ask from me. Thank you for watching this discussion. You are open for the questions now. So if there is any question, you can ask. Okay, there is no question. So thank you very much for having this discussion. Thank you very much, students.